Thank you for introduction, Giovanni. Hello, everyone. My name is Mei Li. I will be presenting on shale fracture mapping by zero-section reconstruction and deep learning assisted geometry analysis. In this presentation, I will introduce how zero-section reconstruction method is applied to map the fracture complexity in shale and what information we can get from the reconstructed fracture network. The natural fractures and bedding planes are common in shale formations, as we can see from this Mei Li shale outcrop. Those natural discontinuities make it possible for hydraulic fracturing to create complex fracture networks. However, it is still unclear that how those fluid-driven fractures propagate and how those newly created fractures interact with the pre-existing ones. To better understand this, we have performed laboratory hydraulic fracturing tests on Mei Li shale sample core samples. The tested sample was prepared from the outlying part of this shale core with the natural fractures and bedding planes preserved in this sample. In addition to those pre-existing discontinuities in this sample, new fractures are expected to be created after the hydraulic fracturing experiment. To better understand how those newly created fractures propagate and interact with the pre-existing fractures, a straightforward way is to map the fracture complexity of the sample. The X-ray micro-CT has been extensively used to examine the internal structure of shale. A spatial resolution down to several microns can be achieved for millimeter-sized objects. However, since the CT scanning resolution is related to the size of the object, scanning a bigger object would result in lower resolution. The 8 centimeter shale cube that we have can be scanned by Phoenix micro CT at the maximum spatial resolution of 110 micron. In this reconstructed CT image, we can distinguish those micro CT detected fractures from rock matrix. However, the fractures below the scanning resolution cannot be captured. Hence, we are not able to see them in this image. So we believe that the micro CT scanning of this shale cube didn't tell us the whole story of the fractures, which can possibly lead us to a biased understanding of the fracture complexity. Therefore, we need to map the fractures at a higher resolution. This target was achieved by applying the zero-section reconstruction method to rock, and the results are published in the conference paper below. The zero-section reconstruction method has been used in the field of medicine and biology for decades. The main idea of this method is to zero-section the object you want to study, and then imaging each thin sections for 3D reconstruction. In order to apply this method to rock samples, we impregnated the rock samples with ultraviolet fluorescent epoxy to better distinguish the fractures from the rock matrix. In order to identify the fractures in the cube that are connected and not connected to the borehole, the epoxy impregnation was completed in 2 steps. In this 2-step procedure, the green epoxy was pushed into the borehole to feel the fractures that are connected with the borehole. And then the cube was impregnated with red epoxy from the external surfaces to feel the fractures not connected with borehole. The epoxy impregnated sample was then zero-sectioned with by a surface grinder, and the newly exposed surface was photographed by a digital camera. This grinding and photographing procedure will remove 50 micron thick layer of material from the sample in each grinding cycle and capture one color image at a resolution of 39 micron. By repeating this procedure through the entire sample, an image stack of 1442 images is acquired. The acquired image stack was registered to generate a smooth 3D reconstruction and then segmented to extract the fracture network in the sample. The cylinder in the middle of the fracture network is the borehole, and the green and red planar feature are the fluid accessible fractures filled with epoxy from the borehole and external surfaces. This reconstructed fracture network was compared to the CT reconstructed one to see if we can get more information from this high-resolution imaging. From this 2D comparison between CT images on the left and the zero-section images on the right, it is obvious that more fractures are kept clearly visualized in the zero-section images. This is because their zero-section image have a higher resolution with a pixel size of 39 micron, and which is about 3 times smaller than the CT ones. This enables more fractures to be captured. And another advantage of zero-section images is the stronger intensity between the fractures and rock matrix. This would help us to better distinguish the fractures. From the 3D comparison between the CT reconstruction on the left and the zero-section reconstruction on the right, the advantages of high-resolution imaging became more obvious. The two fracture networks show very similar geometry. However, the zero-section reconstruction captures the fracture surface morphology in greater detail. So this high-resolution imaging is of great benefit to map the fracture complexity. And in this fracture network, each fractures can be characterized and identified into subcategories. This 3D fracture network on the right was rendered in green and red to distinguish the fractures hydraulically connected to the borehole from the ones are not hydraulically connected. The fractures in green are the hydraulic fractures, and the fractures in red are the non-hydraulic fractures. And in this fracture network, the fractures in parallel and the subvertical fractures are distinct. To better display their fracture geometry, the top view and right view of the fracture network are presented here at the top right and bottom right, along with their comparative CT pre-hydraulic fracturing CT reconstructions. By comparing to the pre-hydraulic fracturing CT, it's easy to identify that the pre-existing parallel fractures are partially open bedding planes, and these bedding planes were extended after fracturing, and some more beddings were newly activated. This subvertical fracture here exists in the sample before fracturing. It is a natural fracture that was further opened by hydraulic fracturing. In addition to the natural fractures and bedding planes, newly generated fractures were also observed, which we can see from the right view. Those two fractures initiated from the borehole and inclined at high angles to the minimum stress direction. We can notice that the newly created hydraulic fractures were generated deviating from the direction perpendicular to the minimum stress due to the strong anisotropy of the tested sample. So with those fractures identified, we are able to study how each fracture contributes to the fracture network propagation. And in order to do that, it is better to separate all the fractures from each other and look at them individually. Since the subvertical natural fracture crosscuts most of the bedding planes, if this fracture can be separated from the fracture network, then the remaining parallel fracture sets can be relatively easier separated. To achieve this target, we introduced the machine learning method to facilitate the fracture separation. We used the supervised learning approach with neural network to classify the vertical fracture pixels from the others in the image. 10 images were chosen from the acquired image stack to be used as training input, and each pixels were labeled as their corresponding class number from 1 to 4 to be used as training output. And this prepared training data was then fed into the neural network model for training and testing. These 3 images show the prediction results of the trained unit model on images of different fracture complexity. We can say The purple lines here are the predicted vertical fractures. We can say this neural network model predicts well on the fractures, which allows us to separate the vertical fractures from the fracture network. And here on the left are the 3D representations of the deep learning separated natural fracture, showing the fracture geometry from the side and front. After this natural fracture being separated, the bedding planes can be roughly separated as well, shown on the right. Through the comparison between the two kinds of fractures, we found that the natural fractures and the bedding planes display quite different roughness feature. The natural fracture is rough and non-planar, while the bedding plane is smooth and planar. And our presentation next will focus more on the roughness quantification of those fractures. This reconstructed fracture network can also be processed to give us a 3D distribution of the fracture aperture. The 2D images here show the thickness of surface mesh of natural fracture and bedding planes. The hotter colors are where the fractures are thicker. For this fracture network, the thickness of natural fracture and bedding planes are in similar ranges from 100 micron to 800 micron. Among the bedding planes, the one closer to the borehole has more high conductive flow channels in red than the others. And for the bedding plane at the bottom right, the fracture is wider on the left side of the intersection. And this is likely an evidence that the natural fracture affected the fluid flow in the fracture network. So what can we learn from this? First of all, the natural discontinuities are the main contributors to the fracture complexity and have the most pronounced impact on fracture geometry. And targeting the natural discontinuities can lead to a more complex fracture network. This zero-section reconstruction method can provide a high-resolution fracture mapping, which allows further quantification of fracture geometries and fracture permeability for fluid flow study. And acoustic emission events can also be located in this fracture network, which can give us an opportunity to study the fracture complexity from the energies perspective. That's all of this presentation. Thanks to our sponsors, NSERC-Energi Simulation, Petronas, CMG, Shale, and Geomechanica. Thank you for listening. I'm open up to questions. Thank you.